In today's video, we're going to be looking at accuracy and precision and how those two words that kind of sound the same are actually quite different. So we're going to start out with this example of a soccer goal and also two definitions. So accuracy is the nearness of a measurement to the accepted or true value, where precision is the nearness of a measurement to other measurements that you have taken. So I'm going to be using soccer as an example for how we might be able to see accuracy and precision in our real life. For this example, it's important to think about accuracy as making a goal, scoring a point. So for soccer, you can score a point, obviously, anywhere inside of this white perimeter. So the goal is to get a goal inside the perimeter. So there are many ways to do that. I could shoot a soccer ball. You're going to have to accept these as soccer balls, even though I know they don't look much like them. I could shoot a soccer ball right here, and that could be a goal. That would be accurate. I could also shoot a soccer ball and score right here. Also accurate. I could shoot another soccer ball and I could shoot right here. Also accurate. The thing about soccer is that to be an actually very good forward, you want to be accurate but not precise. If I were accurate and precise, what you would see is that all of these soccer balls would be in the exact same spot. Now, if they were up here, that'd be great, okay? But as a goalie, you can start to make a move towards the tendency of the striker. And so the goalie might move over and have a better chance at blocking this otherwise very good shot. In soccer, you want to be accurate but not precise. You want to move those soccer balls all around so that the goalie is constantly guessing where you're going to shoot the ball next. That is good accuracy, although it's not precise, right? Those are not precise shots. Could I change these? We've already seen accurate and precise, right? If I was going to be accurate and precise, I would put all of these soccer balls right here together. That is accurate and precise, and maybe not great for soccer, but definitely that is the goal in terms of science. In science, you want precision and accuracy. You want your measurements to always be repeatable and be correct. So in this case, though, I could take some shots on goal that were maybe not accurate, but were precise. Could I do that? Well, sure. This is like one of my specialties right here. I can take these shots on goal and be precise, but not accurate. And then, of course, you could also be neither precise nor accurate. I could shoot one over here and miss, and I could shoot one over here and miss, and I could shoot one over here and miss. And just like that, I am neither accurate nor precise. So we can kind of play with these words and we can think about how they work. So the definitions of accuracy and precision are down here. Accuracy is how close your measurement is to the true value, the accepted value, where precision is how close your measurements are to each other. How close did you get them together? So we're going to do an exercise now with you guys, and we're going to move these little yellow hearts around my different bullseyes in order to make either accurate or precise or not accurate or not precise values. So what we're looking at here are some different bullseyes. I made them myself. I know they look a little off, but I'm going to put some titles over these different bullseyes. So this first one says accurate but not precise. My second one says precise but not accurate. I can have one that says neither accurate nor precise, or I could have one that says accurate and precise. So for the purposes of this exercise, the bullseye is the goal. So being on target is still kind of a miss. You want to be in the blue circle in order to be at the goal, okay? So we want to be on target. So we'll do one together. Let's do accurate and precise. If I was going to be accurate and precise, then all of my shots on this bullseye would have to be at the bullseye and on top of each other. That is precise and accurate. Now, what I want you to do is take some time and on your own paper, first of all, make them bullseyes, put on the labels, and then draw some X's or some hearts or some circles to indicate the correct marks for where you are accurate but not precise, precise but not accurate, or neither accurate nor precise. All right, how'd you guys do? We're gonna look at accurate but not precise first. This one's maybe the trickiest one. If you're gonna be accurate but not precise, then our hearts need to be in the bullseye but not together, which is tricky depending on how small you made the bullseye. I think I can really only fit 2 in here that I can comfortably call accurate but not precise. Remember, that was the different shots on goal that were all over the different areas of the goal, okay, like a good striker would be. Precise but not accurate. So for precise but not accurate, remember precision means that our marks are together, but they are not accurate, meaning they are not on target. So I can move those ones over here like this. And then for neither accurate nor precise, I'm just going to keep my hearts separated from one another so that they are not precise, but also far away from the blue circle, which was my target. So these dots are neither accurate nor precise. So now this kind of a measurement is a little bit subjective because I could make an argument perhaps that these two measurements were in fact precise. Or I could make an argument that these ones weren't precise because I can see the different areas of the heart around it. So in science, we don't like to leave room for argument. We like to have measurement. So the next thing we're going to look at is how percentage error can determine how accurate we really are without the subjective language. So percentage error is how we're going to measure how far off our values are. It's a way to take those little hearts and decide, is it truly accurate? Is it truly precise? And so really what we're looking at is how accurate, how close to our bullseye are our measurements. And so we're going to do that by looking at our percentage error. So this is the equation for percent error. You can see that it measures percentage error, right? In order to measure percent error, we need to have error. So error is our experimental value minus the accepted value. The accepted value is the one that you would look up, that you would know to be true, that would be found on Google. That's the accepted value. The experimental value is the one that you, the scientist, generates. This is the one that's measured in the lab. So we're going to take our experimental minus our accepted, and then notice we have these absolute value bars so that our percentage error is always a positive number. And we're going to divide that by our accepted value and multiply by 100 to get a percent. So this percent error tells us how far off we are. And so we want our percent error small. We want our percentage error to be a small value because that means that we were not very far off. The bigger the value, the worse the data is and the less reliable it is. If I were to measure how far it was from me to a car, I'm estimating, and I estimate it to be 7 feet, but it's really only 1 foot, well, I'm probably going to get hit by that car, right? The farther off your measurements are, the worse it is, okay? The consequences might be different. It's not always you getting hit by a car, but you still want those measurements to be as accurate as possible so that your data is reliable. So we're going to go ahead and try a problem. You can find this problem in your notes. So it says, what is the percent error of a thermometer that reads the temperature of boiling water at 195 degrees Fahrenheit? In order to solve this problem, we need to know what we are being given. We are given an experimental value of 195 degrees Fahrenheit that our thermometer is measuring. We also know the accepted value is 212 degrees Fahrenheit. If you didn't know the temperature of boiling water is 212 Fahrenheit off the top of your head, you could Google it, which is why you know that it is an accepted value because it is available on Google. It's always the same. If you can Google it, if you can look it up, it's an accepted value. We are trying to find the percent error. And I'm going to take a little cheat here and I'm going to say this is my use. I'm not going to rewrite it. That's my use up there. And so now we're ready to plug in. So in my 5-step method, this is step 1, 2, 3 is up here, and then 4, plug in. So now we're ready to plug in. Percent is equal to my experimental value, the one I measured in the lab, 195 degrees Fahrenheit, minus 212 degrees Fahrenheit divided by 212 degrees Fahrenheit. Don't forget your absolute value bars. We want positive numbers. And then times 100 for percentage. So now what I'm going to do is I'm going to take my calculator and plug it all in. So I'm going to say 195 minus 212, and I get about 17. Divided by 212, and I get 0.08 times 100 for percentage, and I get 8.02%. If you got a negative number, then you were not keeping in mind our absolute value. So make sure you keep that in mind. The other thing is that for percentage, just like with temperature, we don't often keep decimal places because we already multiplied by 100, so we already are to 2 decimal places. So 8% error of that thermometer. All right, you guys, that's it for today. I'll see you guys in our next video.